So good morning, team. So we are in the third session of dynamic programming, and we will complete some more problems. Okay. So let's start. So in the previous session, we looked at a lot of DP problems, right? One of them was, uh, like one of the problems we saw was longest common substring. And I said in the previous session that longest common substring is not a DP problem. And the exact reason is that there are no overlapping subproblems, right, in longest common substring, right? So one of the most important properties that a problem has to satisfy that it should have overlapping subproblems. That's where you will have a lot of recomputations, right? You will make use of DP to remove, cut off, prune these recomputations by storing the results of these partial subproblems, right? Okay, let's start our new problem. Longest common subsequence. So here is the problem. You are given two strings, X and Y. Okay, X is of length M and Y is of length N. So what you want to find is the length of the longest common subsequence between X and Y. Okay, what is the difference between substring and subsequence? Substring, you have already said, right? It is a subarray, right? It is a segment of continuous characters. And what is a subsequence? Subsequence is a collection of characters like this. They may or may not be continuous. For example, A, B, Z, A, right? Suppose these characters occur in a string. Look at this. So these are the characters that occur in the string. However, they are not continuous. And you pull them one by one and form another string from it. But these were not continuous in the original string, right? So you can say this is a subsequence of this original string. So what is a sequence? Or what is a subsequence? It is a collection of characters, right, from the original string that occur in the same order. See, A occurs before B here, right? This B occurs before Z here. This Z occurs before A, and this A occurs before this A, right? So this is a subsequence. So you get the meaning of subsequence here, right? Now,
Yes.
how many substrings are there? We saw in the previous session that there are, say, given a string, there are string of size n, there are n squared substrings. I meant theta n squared. Now, can you tell me how many subsequences will be there for a given string of size n? How many subsequences?
2 to the power of n.
2 power n. And why 2 power n?
I said you can pick or you don't pick for any individual.
Very good. So you can pick many types of subsets, right? So subsequences can be mapped to subsets. So how many subsets are there for a given string? So as we saw in the binomial coefficient, it is n choose 0 plus n choose 1 plus n choose 2, so on up till n choose n, right? That is 2 power n. So there are 2 power n, not n power 2, 2 power n subsequences, n squared substrings and 2 power n subsequences. So this is a harder problem. So if you look at it, right? The number of substrings themselves were n squared in the previous problem, right? So it was already polynomial time. The number of substrings itself was polynomial time. I mean, we could have applied any, normal recursive algorithm to solve the problem. There are no recomputations here. It's already in the space of the word of polynomial time, polynomial space. What about this? This is exponential time. So currently this problem is in the word of exponential time, exponential space. I mean, if you want to store it, right? So if you reduce this to polynomial time, that means there should be overlapping subproblems. Here, there were no overlapping subproblems. Hence, we said this is not a DP problem. Here, there are overlapping subproblems, and this is a DP problem. I mean, we will see what is a subproblem and so on, right? As you can see, I mean, think about it. Suppose we took that example, right? Z, B, A, K, K, whatever. Suppose this is a subsequence. Then Z, B, A is also a subsequence, right? This is also a subsequence. Z, B, A, K is also a subsequence. And what about B, A, K? That is also a subsequence. Right? ZAK, that is also a subsequence. So somehow it feels like a lot of these subproblems are related. So there might be overlapping subproblems, right? Okay, anyway, so this is a hard problem, harder problem than longest common substring. So how do you solve this problem? Again, you want to find all subsequences of X, all subsequences of Y, right? Find the common subsequences between X and Y. Find the longest of those common subsequences between X and Y and take the length of it. Oh, why are we interested in only length? No, we can actually compute these subsequences, but here we are just interested in length. For all these problems, right? There is something called solution extraction. That means just given this information, this DP table of length, we can extract this. But in all these DP sessions, we will not look at solution extraction, right? Because it will take more time to explain and right, it's slightly more complicated. So this is called the forward pass of DP. Extracting the solutions is called the backward pass of DP. It is also called backtracing or backward pass. Anyway, so I mean, you can check it in a book, right? So how to extract solutions and all, but we'll majorly focus on forward passes because forward passes take most of the time. So if the forward pass takes n cube time, the backward pass might just take an n time. So hence, this is not the backward pass or backtracing is not computationally expensive, right? It can be n squared, whatever. But typically, it's not computationally expensive. Hence, most of the sharing of knowledge on DP will be on the forward pass, right? Okay, so let's start. So this is our problem, and this is the DP table, right, that we want to construct. So we will see the subproblem. So this is the subproblem. L of ij, length of the longest common subsequence between strings x of 1 to I and y of 1 to j. The first I characters of the first string, the first j characters of the second string. So what are the three types of subproblems in strings usually? Right, there are three types of subproblems. So typically, right, majorly one of these will be used. Prefixes of strings, suffixes of strings, or substrings of strings? Now think about it. So what do you mean by a prefix? Given a string, the first contiguous segment, right? The first part of the string, the front part of the string, and it should be contiguous, right? It is a substring that is at the front portion of the string. That can be the subproblem. Given a string, that means you can write it as dp of I. Here I means the first I characters. What about suffixes? Suffixes means something like this, right? You can say dp of I. Here dp of I means from ith character till nth character, right? That's the suffix. So you can construct a dp table based on this. Substring, that means for a given string, this is the substring, from ith character to jth character. So dp of I comma j. This is for one string, right? This can be the subproblem. So there are three types here. So can you tell me what type is used here? Right? So it's like the first type, that is prefixes. See, we are using prefixes here. Prefixes has one dimension, that for one string, that dimension is being used here. For the second string, this has one dimension. The first j characters are used here for the second string. Make sense? So either you will use prefixes or suffixes or substrings. So here we are using prefixes. I mean, you could have defined using suffixes also here. I mean, not a big deal. They are kind of symmetric. But for some problems, you have to use either suffix or prefix, right? And that need not be symmetric. But here we can either use prefixes or suffixes. We have chosen to represent it using prefixes, okay? Fine. So length of the longest common subsequence between these two strings. The first I characters of X, first J characters of Y. That is L of IJ. So two strings, two dimensions. Maybe three strings, three dimensions, right? Okay, we will not go into generalization. So our aim is to compute L of M comma N, right? Right. Before we start looking at the recurrence, let's look at here we will try to derive the recurrence, okay? Not look at it directly. Okay, let's take one string here with I characters, the first I characters, okay? Because we are always taking the first I characters and first G characters of the second string. This is Y, first G characters. Ith character, I mean the character value is not I, you can see it is at the ith position. So you're really comparing X of I and Y of J. The last character in this prefix and the last character in the prefix of the second string. Okay, so as always, right? I mean, when you define the recurrence, you should always look at either the generic cell I or I comma J or I comma J comma K, right? Okay, so here we are looking at the last characters I and J of these two strings. So what are the possibilities here? The possibility are two things. Now, can you tell me what are the possibilities here? This character.
You're either equal or not equal. You have two
Okay,
options.
good. So either they are equal or they are different, right? The last characters. Okay. If they are equal, what does that mean? What does that mean? Okay, suppose they are
You
equal.
just add one.
So it's at least one, right? If they are equal,
Yeah.
longest common subsequence n, right, for these strings. So it is 1 plus
X, I mean, whatever I minus one, J minus one.
L of I minus 1, G minus 1, right? Because the longest common substring, subsequence is definitely, if they are equal here, you can consider that those characters, right? So 1 plus the remaining x and the remaining y, right? So that is the first I minus 1 characters of x and first j minus 1 characters of y. Take the longest common subsequence of those. Make sense? So that's it. So if they are equal, equal means if x of I is equal to y of j. Okay, if they are different, that means x of I is not equal to y of j, then what do? They are not equal. What do you do now?
Then you look at the last character.
Okay. Suppose it is the case that x of I not equal to y of j. What do you do now? So take the last character of x and y and then
You compare X I minus one to Y J, right?
and why should we do that?
Don't we need to increment instead of decreasing?
So increment what? So what are we incrementing here in indices?
Yes, but I'm so confused because if we got to this point, that means everything before it is equal, but that's not true because they don't have to be equal.
They need not be equal.
Right.
Okay, so again, there are two possibilities. Let's see both the possibilities. In one possibility, you keep x of I, right? You keep x of I, but you do not keep y of j. You remove y of j. Okay? You remove y of j. In another possibility, you keep y of j, but you remove x of I and take the longest common subsequence between these two strings, right? So either you can remove the last character of y here or the last character of x here. See, we are only focusing on these substrings, right? Then in this case, so what are the string lengths here? This is I and j minus 1.
Minus one, yeah.
And this is I minus 1 G.
Okay.
So there are two subproblems. So what should we do?
Plus,
Should we add them?
yes.
Are you sure? Because
Maximize.
maximize.
Maximize, yes.
Add
Yes.
them because they
Or
can
because
repeat
you're
it.
not Yeah, you're not looking for all the combination, but you just need the max. Yes,
Correct.
the largest. Yeah, yeah.
So this is one possibility. This is another possibility. So take the maximum of these two results. That's it.
Mhm.
We don't want to add here because there can be, I mean, answer of this can be here also, right? So we don't want to add them. We want to take the max, whichever gives you the max result. You might say, I mean, why didn't we take, say, I minus 1, j minus 1? Why didn't we take I minus 1, j minus 1?
You have taken care of that last time, right?
No, that was when the two characters was equal. Suppose the last two characters are unequal, they are different.
But you're still taking care of it in the
Where?
last one, right?
No, in the previous argument, x of I was equal to y of j. What I'm saying is x of I is not equal to y of j. I mean, we could have drawn a third possibility here, right? Considering I minus 1 and j minus 1, why didn't we do that? Or should we do that?
This possibility will be covered in the next step in the same case.
Right, see, this possibility is already covered in this and in this problem. Because in the next iteration, if you recursively call this one, it will chop off the ith character and you will also hit L of I minus 1, j minus 1, right? In this subproblem also, in the next iteration, if you recurse, it will also at some point remove the jth character, right? I mean, depending on whether they are equal or not, right? So that is automatically covered, implicitly covered. So you don't need to explicitly cover this. If you want, you can add, right? It won't make it an error or anything.
That's right, because you have maximum.
Right.
Right.
You will not introduce any errors,
Mhm.
right? You will not introduce any errors, but that is not required because it is automatically covered in each of these subproblems. I mean, you can add many more subproblems if you want, maybe I minus 1, see I minus 3, j minus 3 also, if you want. But all these are useless, right? Because they are already covered in these subproblems. So this is the minimum set of subproblems you will have to look at, nothing else. Make sense? So does this make sense?
Hmm.
Okay, so what is the recurrence then? What is the recurrence?
So should be maximized over all the three cases.
See, if x of I is equal to y of
Yeah.
j, then L of I minus 1, j minus 1 plus 1, because
Yes.
one character comes from here,
Mhm.
right? If they are not equal, x of I not equal to y of j, then either you remove the jth character or you remove the ith character, right? There are two possibilities, right?
Yes.
And then take the maximum of these two. Should you add plus 1? No, because the characters are different,
The last one does not equal.
right? Okay, then what is the base case? So once you got the recursive case, what is the base case? If the first string has kind of no characters, or the second string has no characters, the longest common subsequence is definitely 0, right?
Mhm.
One of the strings is empty string, null string, empty string, then LCS length has to be 0. Hence, you have this or means
Uh,
the 0th row or the 0th column, right? 0th row and 0th column both will be zeros. Make sense?
the professor, a question here.
Yeah.
So why the second part of the equation is plus instead of maximize over all of the three?
Oh, okay. So I added this because it won't affect the result, right? So either this will be correct or this will be correct. One of them will.
Yeah, that's true. That's true. Logically, yes.
Right.
Yeah,
I mean,
yeah,
you can
mutually
also,
exclusive, yes.
yeah, you can also use a max if you want, but it won't.
Yeah, okay, gotcha. This is probably easier because you have less computation.
Right.
You don't have to compare, yes.
Okay, makes sense. This is our
Yeah.
LCS recurrence. And what will be the dependency diagram? So suppose this is your I comma j cell. So that depends on I minus 1, j minus 1. So this is I minus 1 j. This is I j minus 1. Right? I mean, for every cell, it need not depend on all three cells. But we have said that at most, right? I mean, depending on like whatever might be x of I and y of j, right? It should depend on some of these three. Some of these three cells. Make sense? So that's your dependency diagram. Okay, so here is the pseudocode. See, once you have the recurrence, you can convert it into the pseudocode very easily, right? So here it says I is equal to 0 or j is equal to 0, then length is 0. It's very simple. This is 0th column. All cells in 0th column are initialized to 0. All cells in 0th row are initialized to 0. And then you have two for loop, right? I1 to m, j1 to n. Compare whether the characters are equal or not, right? The last characters in that prefix, x of y, y of j. If they are equal, use this, right? The first possibility we discussed. If they are unequal, you take the max of the two possibilities here. Return L of n. See, writing pseudocode is trivial, right? It's the recurrence that is the headache. Okay, so here is a table. So how should we analyze this? Okay, let's try to analyze maybe the longest common subsequence between these two strings. So Einstein and Newton, right? So here the answer is 3. Let's see how we get this. So what is LCS at this cell, right? We compare the characters here. N is equal to N. So LCS of this cell is LCS of I minus 1, j minus 1 cell plus 1, correct? Fine. What is the LCS of this? Okay, let me add plus 1 here, plus 1. What is the LCS of this cell? I and O, they are different, right? They are different. So you take the max of I minus 1 j and I j minus 1. So you take the max of these two. You can pick anything here, right? Because in this example, both are equal. Suppose the max was this, right? Okay, so suppose the max was this. Let's start with this. E and O, there is a mismatch, right? E and O, there is a mismatch. So the value at this cell is the max of these two cells. For simplicity, we will assume that the max was this, right? I mean, we can arbitrarily break the tie if they are equal, right? Okay. So suppose we came from this. So you have T here, then O here, then max of these two. They're different, right? The characters are different. So max of these two, that is this. Max is this. Okay. Then T and T, T and T, the characters match. If the characters match, it has to come from the diagonal cell. Value of LCS here plus 1. Make sense? So, I mean, in none of these, we added 1. So we added 1 here, we added 1 here. Look at this. Okay, then S and I'm not able to see the characters above. Let's put this down. So we have S and W unequal. So max of this and this. Suppose we pick this, right? S and E unequal, max of this and this. Suppose we pick this, right? N and E unequal, max of these two. Suppose we pick this. N and N diagonal. It comes from the diagonal plus 1. And here you know that all these things, right, cells in 0th row and column are zeros. Make sense? So can you tell me what is the longest common subsequence? Here, right, plus 1. N character match, so N. And then here, T character matched, so T. And here, N character match, so NTN. NTN need not be the only longest common subsequence. There can be many other longest common subsequences. See, we arbitrarily broke the ties and all those things, right? But if you consider all possibilities, there can be a lot of, answers, right? The solutions. But here we are just saving the length of the longest common subsequence. But if you also save which cell you came from, right, and backtrace, like I showed here, you can also construct the solutions, right? See, backtracing is just going in the opposite direction where you came from, right? Again, comparing characters and all. So here we constructed the solution, that is NTN is the longest common subsequence, one of the many longest common subsequences probably, right? Anyway, so this is backtracing. This is the backward pass. Backward pass, as you see, it's not that complicated. It is just kind of one scan, right? You didn't even had to look at every cell in the DP table. It's just one path from this node to maybe one of the base cases. All these are base cases, right? So it can be anything. It can be like this. It can be like this. But you'll pass through one path. Okay, we will not formally cover backtracing or backward pass, but you might have gotten the idea here. Questions? Any questions? Right? So this is the longest common subsequence, length of longest common subsequence. And can you tell me what is the complexity of this? 2 dimensions, Mn. M times N. Here M is the size of the first string, N is the size of the second string. What is the complexity? Quadratic. Quadratic. Now think about it. How many subsequences were there? 2 power n for, one string. Suppose the 2 strings are of the same length, right? Suppose m is equal to n, then this will be n squared. we reduced it to n squared. So ordinary recursion or ordinary brute force approach to solve this problem, you will have to compute all subsequences, right? It will be minimum of 2 power n, minimum. And if you're scanning each subset and processing, it can be more, but minimum of 2 power n. Look at what we achieved. This hard problem of longest common subsequence we solved in theta n squared, right? Theta n squared. So look at the beauty of this. And why theta n squared? Because the best case, average case, worst case, everything is n squared. Because we are filling the table. Right? Filling the table, like whatever strings you give, the complexity will be m. Right? There is no best case, worst case separately. Right? Everything has the same complexity. This is beautiful, right? So now we reduced a problem from this polynomial time word and pulled it back to exponential time word to polynomial time. And in general, DP does this a lot. So a lot of problems will be taking exponential time if you use a normal straightforward approach. And if you look at a lot of articles, people write the first straightforward approach that comes to their mind. Okay, so take all subsequences, run them, execute them, show the results, right? Typically, lots and lots of websites, articles, right? They just do it in a straightforward brute force manner. However, now you understand that. So DP is like a channel that can pull all these problems to polynomial space. If you use DP, you are bringing, right, a lot of these problems, not every. TSP is still there. Even if you use DP, it will still be in, right? Some DPs can be like this. It's in the exponential space domain, TSP, but you can come up with a DP algorithm to solve the TSP problem, but still it will be exponential. It's better than, see, the normal algorithm for TSP is n factorial, but using a DP, you can bring it down to 2 power n times n squared, but still it is exponential. It is definitely better than brute force, but still it is exponential. In general, DP is always better, right? And in most cases, it is better than the ordinary brute force approach. However, for many problems, why it is super famous and most beloved algorithm design technique is it can pull down all these problems to polynomial space, right? So a lot of, say, 2 power n algorithms can be brought down to n squared, n cubed, n, right? This is beautiful. And Fibonacci, right? If you do a normal recursive algorithm, phi power n, golden ratio, right? Phi is golden ratio, phi power n, that was brought down to n. Of course, these need not be the best algorithms, right? There can be other algorithms that can, pull the complexity down, but still these are way better. And this is a technique that can work on thousands of problems, not just one or two. I mean, there can be specialized techniques for each problem that can reduce it further, but the beauty of this is so generic that it can work on thousands of problems and bringing them to the polynomial world. Okay, let's move to want to cover edit distance also, but what we will do is right now we will skip. If we have time, we will come back. Let's move to knapsack. So I have not covered this problem, right? Knapsack problem. This is a beautiful problem, heavily used in operations research, where they want to maximize, minimize, and so on. So what is a knapsack? It's a bag, right? It's a bag. It's just a bag. Okay, let's understand this problem. Given a set of n items numbered from 1 to n, 1, 2, 3, 4, so on, up to n, such that item I has weight W of I and value V of I. That means the first item has weight W of I and value V of I. The second item has weight W of, so I should have considered this 1, W of 2, V of 2. Third item, W of 3, V of 3. So on, right? W of n, V of n. So every item, right? So it has some weight. Maybe consider a 1 kg gold bar. The weight is 1 kg and the value is, it's extremely precious, right? Maybe thousands of dollars. And similarly, you have, say, 1 kg of rice. So you store the weight as 1 kg, but the rice is not as expensive as gold. So you have a lot of these items with their weights and values. Okay, what is the goal? You have a knapsack. Knapsack is just a bag, right? Knapsack is a bag. You want to add some of these items, right? Some of these items to the knapsack, which has a capacity W, right? It has a capacity W. It can hold at most W weight, right? Okay, so you can add items such that the sum of weights is not capital W, and you want to maximize the total value of all items. You want to maximize the total value of all items. That means, think about, say, aircraft, airplane that wants to transfer some items. And suppose you had this option, right? Typically, there will be a separate compartment where you can store items that are not related to passengers. Passengers, weights are different, right? I mean, they have their bags. That's mandatory for. So that's different. So they have to carry those weights. Apart from that, there will be extra space that such that they can carry some items of precious value, right? Just for transportation. So what they want to do, what they prefer to do is they want to keep those items in that extra compartment such that they want to maximize the total value. They don't want to carry each and every item given, right, to them. Make sense? So they want to maximize the total value. But the weight, total weight is kind of fixed. You cannot have more items than this weight W. This is heavily used even in lorries, trucks, and in many other cases, right? Okay. So what's the aim? Identifying a subset. See, subset. How many subsets are there? 2 power n. So this is also an exponential problem. So we want to identify a subset of these n items such that the sum of all weights is not greater than W and the sum of all values is maximum. So this is a maximization problem or an optimization problem heavily used in operations research. There are two types of problems here: 0-1 problem and unbounded version. What is 0-1 version? Each item can be considered only once. That means if you decide to add an item, you can add it only once. Either it is available or it is not available. Done. Period. Right? 0 or 1. 0 means you will not consider the item. 1 means you are considering the item only once. Okay, what is this unbounded variant? That means each item can be considered infinite number of times. Assume that, suppose it is a notebook, right? You have infinite copies of a notebook, infinite copies. So you can decide when to stop, right? So something like that, right? Unbounded or unlimited copies of that item. So copy means what? Suppose you have a fifth item is the notebook, right? So the weight is say 20 grams and the value is say $1. So you can repeat the same weight and same cost unlimited number of times. Okay, so that is the unbounded version. So we will cover both the versions, 0-1 version, unbounded version. Okay, let's take an example. N is equal to 5, weights are these, values are these, and capacity is 12. Now let's look at both the versions. 0-1. Maximum total value is 50. Can you tell me how? How is it 50?
9, 3, and 2, or not 9, 7, 3, and 2.
Okay, 7
So the-
plus 3 plus 2 is 12.
So then 25 plus 15 plus 10
25
is
plus
50.
15 plus 10 is 50. Great. So you want to add items 1, 2, and 3 into the bag, into the knapsack, right? So this is the capacity. It is equal to this capacity, right? Ideally, it is less than or equal to. But up till this point, you can keep adding. But once it is greater than 12, you cannot. Right? And total value is add all the values here. You get 50. So maximum total value is 50. What about this unbounded version? The maximum total value is 60. How?
You just repeated the first item for 6 times.
Right. Okay, 2 plus 2 plus 2, 2 plus 2 plus 2, right? 12. And
You count 6 times.
10. 6 times 10 is equal to 60. Right? You are repeating this item again and again. There are multiple copies. Make sense? So this is one example. So similarly, you can come up with, many other examples. And the subsets need not be unique. There can be multiple subsets, right? That have the probably not greater than 12 and, right, have the same max value. There can be, right? So here you're just interested in one such subset or just the total value, right? So here we will just aim for finding the total value. And as I said, this is the forward pass of DP. Using a backward pass that we will not see, right? But it will be similar to what I discussed earlier for LCS. Using a backward pass, you can find the exact subset. Okay, but we will not look at it. We will just look at how to identify or determine maximum total value of the items. Okay, so let's start. This is our problem.
Sorry, Professor, I have a quick question. maybe not very relevant to this, but I think this is kind of if we're talking about a lot of optimization problems, it's optimize something subject to something, right? Like you maximize the value subject to the capacity limit. So did people do some research to find the relationship between this kind of discrete mathematical problems, right? So, but often the optimization issue is for continuous functions. Did any people do any research in that regard to connect these two together?
Very good. So in fact, dynamic programming, right, is heavily defined for continuous functions. If you look at 60s and 70s papers and analysis, dynamic programming, they use it for continuous functions. However, in the world of computer science, right, we computer scientists want everything digital.
Yes.
Right, so we don't work with continuous functions, we work with discrete values. So hence the same dynamic programming that mathematicians, right, they can work on, they are working on continuous functions, we work on discrete values only. So it's the same idea and it is related and there are results. But for computer scientists, it is extremely difficult to understand that continuous math, right? It's because it requires hardcore knowledge and depth in mathematical analysis that we lack, right? And similarly, mathematicians, they are not that interested in computation. They are interested in analysis, right? Hence, just focus more on those continuous functions, and you don't care about time complexity, how much time it takes, or whether it can be programmed or anything.
Okay, thank you.
Yes, very good question, very good question. Fine. Let's look at subproblem. So here is our subproblem. Before we move to subproblem, right? So can you tell me, how do you solve this problem in general, brute force way? I think we looked at this problem before, right? In brute force, did we?
It's not in brute force, I believe. It's in very early stage. I forgot what. It's brute force, but we did, yes.
Oh, okay, I see. So, like, what is one idea? One idea is like dead simple idea, brute force, right? Exhaustive search. Try to find all possible subsets of these n items. There are 2 power n subsets. Let's focus on 0, 1 version first. There are 2 power n subsets. Take each subset, add all the weights, add all the values. If the weight, sum of weights is less than or equal to knapsack capacity, right? Put it in the participant list or candidate solutions list or whatever. Keep doing it. Once you get the candidate solutions, take the subset that maximizes the value. Done, right? That's your brute force algorithm to solve this 0, 1 version. Unbounded, I will leave it to you, right? You can think and try to find how do you solve this unbounded version in a brute force. As you see, the simple brute force approach is exponential time, right? 2 power n, minimum 2 power n time. And we want to do it in a better way. Let's see how. Excuse me. Let k of ij be our subproblem. K of ij. Why do we have two indices? Let's see. So this is the maximum total value the knapsack can hold for the first I items. I means first I items, and j means the utmost capacity is j. Right? The first items, you are considering items 1, 2, 3, so on up till I, and capacity at most J. So what does this mean? With capacity at most J. So here you're assuming a capacity at, what is the meaning of this? What is the meaning of capacity at most J?
You mean the
Like
weight,
the
right?
maximum
The weight.
knapsack size.
So you can say that the sum of weights, right? That is W of 1 plus W of 2, W of 3, so on up to W of I should be less than or equal to J. That is the meaning of capacity J, at most J. Make sense?
Okay.
Right? So this is the meaning. So that means you're not allowed to have any items
J, does that mean each item has a maximum weight of J or the total of them?
No. So here, okay. So I shouldn't say W1 to WJ. I should say that, so assume that you have a capacity, right? That
Yeah.
capacity is not more than G.
Okay, that's good.
Right? I think this is a better way of explaining things, right?
Okay.
But you should focus on only the first I items. And capacity shouldn't be more than G. So let's assume just this as, one more knapsack, right? Knapsack with capacity at most G. Let's not consider which items are considered here, okay? Make sense? Any subset of the first I items that can go into this, right? When we say first I items, it means any subset of first I items, right, can go into this with capacity at most J. Make sense? Okay. Now, this is given to us anyway. W of I array, V of I array, right? This is an array of values. Okay. Fine. Then we have the objective subproblem, that is K of n comma W, right? Total number of items is n. That means the number of rows is n, number of items, right? Number of columns is W. This is the knapsack capacity W, knapsack capacity.
A quick question, Professor.
Yes.
Are those items, the weight of this item is sorted or unsorted in general?
Oh, good. So this problem works for any items. They need not be in sorted order. Okay. They need not be in sorted order. Make sense? So, okay. Let's continue. So here are our recurrences. I mean, we will try to understand this, right? We have the 0, 1 version. We have the unbounded version. And these are the recurrences. And can you see the differences between these two versions? What's the difference? The difference is only here.
Only one, yeah.
In 2 characters, -1. Look at the beauty of these recurrences, right? The difference between the recurrences for 0, 1 and unbounded is only in 2 characters. Okay, then we will need to understand these recurrences. How do we get these, right? Why do we get these? And why is the difference minimal? Right? So take a, complete look at this, right? Kind of remember it. because we will try to derive this recurrence. So this is k of ij is equal to, or do not worry about the base case and all, we'll come to this later. Max of k of I minus 1 j, and then I minus 1 j minus w of I, j minus w of I, and plus you're adding the value of the item. You will consider this only if j is greater than or equal to w of I. And this is understandable because you don't want this to be negative.
Mhm.
But okay, how do we get this? Right? How do we get this? Kind of, weird recurrence. So let's go to our whiteboard. You will derive this recurrence, okay? Annotate. See, k of I comma j. So here, first we will focus on 0-1 version of the knapsack problem, okay? 0-1 version of the knapsack problem. Now, I see that there are two possibilities. Can you tell me why?
Yeah, if the last one, right, if it's too heavy, then you never put into this capacity. So you don't need to consider it. You move on.
Mhm. So let's say, like before considering the weight or not, let's decide on just two possibilities, right? Without consideration of weight, value, anything. Very basic possibility. So we know that these represent the first I items, right?
Mhm.
First I items. So there are two possibilities. I item is not considered, not selected. I item considered, that means selected in our subset, right? That's it. These are the two possibilities. We either select the ith item to be in the knapsack, or we do not select the ith item to be in the knapsack. Only two possibilities. Think about it. So we said there are 2 power n total subsets, right?
Mhm.
What does it mean? The first item, you will either consider it or not consider it. Second item, you will either consider it or not consider it. So on until the nth item, you will either select it or not select it. So choices are 2 times, 2 times, 2 times, so on up till, right? If you repeat this n times, you get 2 power n. Similarly, we are here considering whether the ith item is considered or not. There are two possibilities. If you have this kind of a binary tree, remember that's how you get 2 power n. Okay. Now these are our two possibilities. How should we go about next? If the ith item is not considered, that means you will not add ith item to the knapsack. Okay?
That's okay.
So
I minus 1. Okay.
So it will be I minus 1 because ith item anyway you're not considering,
Mhm.
but you still have the knapsack, the exact same knapsack, right?
Mhm.
G. So it is this. If you don't consider the ith item in your knapsack, k of ij is same as k of I minus 1j. Correct? So does this make sense?
Yeah.
See, ith item is not considered here. Hence, we have I minus 1 items now that you can recursively check whether they are considered or not. Make sense? So simple. This is simple. Now, if you consider the ith item, then what happens? If you consider the ith item, right, you are adding, that means you are adding in the knapsack the ith item. If you add the ith item, this is the maximum total value, right? That total value is V of I plus, correct? Because you added it, you need to consider V of I value of the ith item plus, right? What are the remaining items? Still I minus 1, because you already looked at ith item, you have added it. Now you need to look at the I minus 1 items, same as before.
Okay. But you take the value Vi out of the J.
Exactly. Now your capacity was J before. Now you added the ith item. Now your updated capacity will be J minus W of I. Correct? See,
no,
the
V of I, right?
No, capacity.
Oh, sorry, I'll take it back. Yes.
It's the weight.
It's not, yeah, the weight, yes.
See, this takes weight W of I. So you need to reduce W of I from this knapsack capacity. This is what is remaining now. J minus W of I is remaining amount that you can add. So recurse. So does this make sense?
Yeah.
So if the ith item is considered, the value will be, the maximum total value will be V of I plus K of I minus 1, J minus W of I. Got it?
Yeah.
So what do you do here? So either this possibility, right, will happen, or this possibility will occur. So you take the max. You don't know, right, which possibility can occur. Just take the max.
Interesting.
And okay, like why do we have J minus W, J greater than or equal to W of I? Simple. I mean, you want to make sure this is non-negative, right?
Yeah.
You want to make sure that you add it only if there is capacity. Else you cannot add it. So make sure this is greater than or equal to 0. Okay, so this is how you derive the recurrence. So taking a subproblem and trying to look at the last item or index or character in a string, whatever. So take the end item, end element, and check how you can recursively compute it, focusing on that last element. I mean, remember in LCS, we looked at the last character of X, X of I, the last character of Y, Y of J. And then we either removed it or inserted it, so on, right? And we recursively computed the problem. Here also, I comma J, you are dealing with the ith item. That's your last item. So here I mean, there are only two possibilities. Either you will add it to the knapsack or you don't add it to the knapsack. If you don't add it to the knapsack, it's easy problem. If you add it to the knapsack, take the value of it and reduce the capacity by W of I. Done. and recursively compute this. I mean, in every DP problem, the core idea will be the same. So does this make sense? Okay, so that's your recurrence. Right? That's how we have this recurrence. So this is ij greater than or equal to 0. If so what is the meaning of this? Either I is equal to 0 or j is equal to 0. If I is equal to 0, there are no items, right? Then the value will be nothing, 0. If the capacity is 0, still you cannot add anything, so the value will be 0. If I is equal to 0 or j is equal to 0 is same as saying ij is equal to 0. Right? So the base case is 0. Again, you should always try to find the subproblem first, compute the recursive case of the recurrence first, and then think about the base case of the recurrence. Right? This is the step-by-step way you need to, right, analyze. Okay. Now, so as I said, the only difference between 0, 1 and unbounded is just in -1. Can you tell me why, when we remove it, it will be the recurrence to unbounded version? So the idea is this. So what is the meaning of this case? This case means we are adding ith item to knapsack. Correct? Knapsack. If we add the ith item to knapsack, we are saying that that ith item is no longer available. Correct? In 0, 1 version. But in unbounded version, when you add an ith item to knapsack, you won't decrement this because you can still add another instance of the ith item, another copy of the ith item, right? You can add unlimited number of copies of the ith item if you want. So hence, we do not decrease that, okay, we are done with the ith item. Make sense? So we do not decrement this. We keep this as it is. Because in the next instance, if you think if this still works, you can add the second instance of ith item if you want. Right? So this is the reason we are not adding -1 here. Or you might say, okay, if we once add the ith item, I mean, don't we repeatedly add the ith item until all the items will just be the ith item? No, because this makes sure that you cannot go on forever. Right? You cannot go on forever. You will have to stop at some point. Make sense?
Yeah, this is very, very good in the sense that you basically optimize with less weight with I items. Then if that I is very good, the last one is very good or with very much value, then you will add last.
Right. So, and so here is another so as Edward pointed out, right? So here is another point. You might say that the answer or the result might depend on the ordering of the items. Maybe, right? It might depend on the ordering of items. will you get two different answers when you run it if you change the ordering? No. No. Though it might feel like, right, maybe the answers will be different. No, because these constraints, right, whether you have enough capacity or not, and so on, all these things, the weights and capacities and the values and so on, and taking the max at every point will make sure that it doesn't matter, right, whatever is the order. It's like taking min in an array. If you shuffle the array, unsorted array, shuffle it, permute it, will the min change? No. Right? Similarly, as we are using a max here, the max value does not change. Okay? So it does not matter. The order of items do not matter. So this is why you can see the beauty here that you need not have the items in the sorted order of weights. Right? Any permutation of it works fine. Because it's like taking min of an array or max of an array. It doesn't matter. Right? If you shuffle the elements, the answer remains the same. Okay. Fine. Next, let's go to dependency. Dependency looks like this. You can plot it easily, right? Next algorithm. The pseudocode is like this. If you only include line 5 and not 6, then you will get the pseudocode for 0.1 version. If you include line 6 but not line 5, then you get the unbounded version pseudocode, right? See, the same pseudocode, either comment this line 5 or comment line 6, exactly one of these two lines, right? You will get a algorithm. See, this is kind of reuse also, and it's beautiful, right? And how they are related and everything, just in 2 characters, -1. So we looked at how to analyze a table, right? We went into one particular cell and we looked at all those details, right? You can also backtrace, right, in these tables in the same manner. So how did you get 50 here? So 0.1 knapsack. So you take this cell or what? 12 minus 15, right? So what is 12 minus 15? So that's not possible here, right? So this value comes down here directly. So similarly, this cell, 12, so that comes from this cell, or 12 minus, what is it? 12 minus 9. 12 minus 9 is 3, this cell. So 15 plus 13, right? See, so you want to do j minus w of 4, j minus w of 4. I mean, this was the cell, right? Third, that is 12 minus 9. And you need to add, like, to whatever value here is, you need to add the value of the item, that is 13. So 15 plus 13 is still less than 50. So, right, this value will be used. Okay, now let's think about one cell before. So how do you get 50 here? So either take this cell directly, right? I minus 1j, or you do 12 minus 7. What is 12 minus 7? It is 5. 12 minus 7 is 5. So take the value of the third item, 25. Add it to this. So 25 plus 25, right? 50. So max of 50 comma 25. So it's 50. Right? So you get this 50 from this cell. And so on. So you can evaluate every cell in this way, right? Follow the recurrence. Follow the recurrence. Complexity NW. Okay. And do we have time? Probably not. See, there is a better way to write this unbounded knapsack also, using only one dimension, but we will not cover that. Okay. And similarly, you might have heard about coin change problem, right? Suppose you have coins of different denominations, maybe denominations C of 1, C of 2, C of 3, so on up to C of M. And suppose these denominations are in the decreasing order, right? Sorted order. 9, 5, 1, something like that, right? You want to compute the minimum number of coins to make a change for n amount. That means these are your denominations. This is C of 1, C of 2, C of 3, C of 4, right? N is equal to 11. You want to give change for 11. Right? What is the minimum number of coins, right? You can choose from these denominations to make 11, right? The answer is, say, 6 plus 5, correct? 6 plus 5
Yeah.
is min coins is 2. Or you
Can you
yeah.
Sorry, can you repeat the coins like say 9, 1, 1, 1 twice to make an exchange?
Oh, okay. Repeat, Edward.
So what I'm trying to say is, say here, right? You have 9, 6, 5, 1. I want to get 11. Can I have 9 and 1, another one? So
Right.
that means one has to be repeated once. Okay. Okay.
You can have
I'm trying to understand the question. Yeah. Thank you.
can have something like this. You can
Okay.
have
Gotcha.
something like this, right? 11 coins with the same denomination, but the
Okay.
number of coins here is 3, number of coins here is 3, number of coins here is 11, and there can be multiple combinations of answers. But here you want to minimize the number of coins,
Of course.
right? So 6 plus 5 minimizes the number of coins. And you need to assume that there are infinite copies of 9, infinite copies of 6, 5, and 1.
Is
So
that kind of inverse problem of the knapsack?
exactly. It is like our knapsack problem. There we were trying to maximize the value. Here we are trying to find the minimum number of those copies, those instances.
Yes.
Right? So it is slightly related. Not exactly same problem, but related problem. So knapsack and coin change, they are kind of related. See? So hence this knapsack, you need not remember only the problem, right? It can appear in many variants. So this is also kind of, you can say, application of knapsack, or you can consider knapsack as the application of coin change, some variant of coin change, and so on. So the point is, a lot of problems are related. So if you know more solutions to more problems, when you see a related problem, you should be able to solve it, right? So trying to reuse the solutions from existing solutions. Again, I do not have time to quickly cover this or anything, but so I'll just give you one minute, high level idea of right, to solve this problem. So M of I is the minimum number of coins to make a change for value I. So the recurrence will be something like this. I, you want to make change for I, right? So what can you do? You can either consider C of 1. If you consider C of 1, say C of 1, the remaining amount you need to make is I minus C of 1, correct? If you
Mhm.
consider C of 2, the remaining amount you need to make change for is I minus C of 2. So on C of M, I minus C of M. Right? So these are the subproblems. So M of I is same as M of I. So these are all the subproblems. You used one coin here, right? So plus 1. You use this coin here, right? So plus 1. So here, which coin used is not important. You used one coin, so adding plus 1 is important. Make sense? So that's the idea, and make sure that this won't go negative. So that's why we have this. Okay. So that's it. This is your recurrence, and if you solve it, that's the solution. And you understand how the recursion happens, right? See, you can make so if you have I amount, you should have used either C of 1 or C of 2 or C of 3 or C of M, one of these. Once you use that coin, the amount you have to make will reduce. So if you use C of I, the amount you need to make now is I minus C of I, or I minus C of J, whatever. Okay, for all possibilities, M possibilities. In every case, you're adding 1. So these are the, M possibilities. And your aim is to minimize the number of coins at a min. Done, right? So that's your recurrence. Okay, so that's your recurrence. You can see the pseudocode and try to solve this problem. All right. So that's it. So the answer is still kind of quadratic here in 2 variables, M and N. So anyway, so we are done with knapsack problem, LCS, coin change, right? So in the next session, we will look at another topic. Okay, so let me